Aaron, shout out. Hope you're having a good day, man. I guess I should shout out the rest of you. Who else was it? Anna Grace, Holly, Rachel, Colton. Thank you, Colton. Colton, yes, I did have to be reminded about you. Sorry about that. All right, so yeah, that's like audio recording evidence that I forgot. All right, so today what we're going to talk about are called determinants. And we've got this thing called Kramers rule. You know, you may be thinking to yourself, well, how the heck do matrices fit in anywhere to what we were doing? Like, where the heck did this come from? And look, it seems like we just, stopped chapter 3 and then said, okay, now for something completely different. And went on to a completely new topic, which was true, but we haven't really studied the application of this yet. And that's what we're going to kind of get into today. Now, to understand the application, we need to understand how to find what's called a determinant. A determinant. Now, a determinant is a value associated with a matrix. Just like, you know how slope is a value associated with a straight line? It's like a measurement of the steepness of the line, right? The steeper the slope, the higher the number, right? Just like the R value is a strength of relationship number, right? It's just a number associated with a linear regression. And you just got to be able to interpret that number. Same kind of thing for a determinant. A determinant is really just a number associated with a matrix. Okay? The determinant will tell you things. It will tell you things about the matrix. And only certain matrices have determinants. For example, every square matrix has a determinant. Okay, every square matrix has a determinant. Okay, what does that imply about non-square matrices? They don't have determinants. Okay, so if I say give the determinant of a 2 by 3, well, that's a dumb question because there are no determinants of 2 by 3s. Every square matrix, n by n, so 2 by 2, 3 by 3, 4 by 4, and so on, has an associated value called its determinant, shown by straight vertical brackets. The notation here almost looks like absolute value-ish, in that it has those straight lines. Don't associate anything to it as the value though. That's what the notation looks like. Basically, just take off the little wings of the bracket. The determinant is a useful measure, as you will see later on in this lesson. So how do we find the determinant? Well, we're going to start small, and we're going to say, let's find the determinant of a 2 by 2. A 2 by 2. Here is the determinant of a 2 by 2. The determinant of a 2 by 2 matrix is the difference of the products of the diagonals. I'm going to say that again. The difference of the products of the diagonals. So almost like I'm taking the cross products and then subtracting them. Taking the cross products and then I'm going to subtract them. So for example here, I am going to take 1 times 4, and then I'm going to subtract away 3 times 2. So the determinant of that simple 1, 2, 3, 4 matrix is negative 2. 4 minus 6 is negative 2. Okay? So, algebraically showing you here, I would take A times D and subtract away C times B. Okay? You always start with what's called the main diagonal. The main diagonal, we haven't used that term yet, but the main diagonal of any matrix is the one running from the very top left corner down to the bottom right corner. That's the main diagonal. Okay? So you start with the main diagonal, and then you subtract away the one running from top right to bottom left. The determinant of don't confuse it with absolute value. Kind of talked about that. All right, find the determinant of this matrix. Okay, not so bad. It's always funny. For some weird reason in academic challenge, we always get in some of the math section. I don't say always. There's usually once or twice a season where we get a question about matrices. And like I said when we started this chapter, like we're the only school left around that still does matrices, and like we always crush those questions because usually they're really easy, but you don't know how to do it unless you know what it is. Like they say, find the determinant of this matrix. That's a pretty simple operation if you know how to do it. Okay, so what's the operation? Well, it's just literally 1 times 8 minus 4 times 5. Oh, well, that's super easy. 8 minus 20 is negative 12. I mean, you can do that in seconds, right? That's the determinant of that matrix. But if you don't know how to do it, you're stuck, right? Now, we have no idea what this means yet, right? We have no idea what this means. We just know this is the determinant is equal to negative 12. Okay, why don't you guys do this one? Of course, I give you one with this one. Of course. All right, so again, we take the cross products and we subtract them. So 0.2 of 5. What's 0.2 of 5? 1. And we subtract away, what's negative 0.3 of 30? Heard a couple different answers. Negative 0.3 times 30, negative 9. So my determinant is 10. The phone. I did though. I swear I did. JGC. Hello. How you doing? Can you call Tom Grubb's room? She transferred classes, but she's technically still on my roster. Tom Grubb's room. Yep. Bye. Questions about that one? We good? Wait. All right. So determinants, pretty easy to find, right? Just a simple operation, especially with a 2x2. Now, we can use determinants to actually find systems of equations. See, this is how it's going to tie in. Remember chapter 3? Remember everything we did in chapter 3? And I said, okay, there's 3 ways to solve systems of equations. Graphing, substitution, elimination. I was kind of fibbing, because there's a 4th way. Using matrices. Okay, using matrices. And actually, there's 2 ways to solve them using matrices. You can either use matrices to solve them by Kramers rule, or you can use matrices to solve them by way of matrix equation, which we'll learn in section 4.5. So in sections 4.4 and 4.5, we actually get to apply what we knew in chapter 3 to what we've learned in chapter 4. You can use the determinant of a matrix to help you solve a system of equations. For 2 equations with 2 variables written in, okay, so make sure you make note of that. It's got to be in standard form. Has to be in standard form.
I'm good. I'm playing along. I feel like that's always awkward when you can tell that like you're the person shutting the door.
I know.
And it's like awkward that you're shutting the door because of them.
That's okay.
That's like Mrs. Delaney. She did that when we went to vote. She did.
I saw her do that. All right, so it's got to be in standard form, right? AX plus BY equals C form. Standard form. You can construct a matrix out of the coefficients. Take a look. Once you get your 2 equations set up in standard form, obviously they're both going to be AX BY equals C form. You're going to have 2 coefficients off A, 2 coefficients off B, and a set of C values, the constant values. Okay? So what you can do is kind of like remove those coefficients and use it as what we call the coefficient matrix. Pretty simple in its name. The coefficient matrix. Those are just the values of the coefficients of x and y. We can obviously find the determinant of that. Yeah, but how does that help us? Well, we have this thing called Kramers rule. Thank you. This is Kramers rule for 2 equations. This is the very bottom of your front page. This will solve you any system of equations, any 2x2. Yet tomorrow we will learn Kramers rule for a 3x3. Okay, it's a little bit more involved. We'll spend the entire day doing a couple problems with a 3x3. Now, Kramers rule for a 2x2. Notice the setup. They both have to be in standard form, x, y, then constant. Okay, so the system has solutions. X equals, now take a look what's happening here. I've got a determinant on top as noted by the vertical lines. I've got a determinant. Now, what's in that determinant? Well, for x's, I take the coefficients off the y's, but as for the coefficients off the x's, I replace those with the constants. Okay, I replace those with the constants. For the y coordinate, and then I divide it by d, which I'll talk about in a second. And then for the y coordinate, I take the determinant of, well, I keep the x coordinate coefficients, but now I replace the y coordinate coefficients with my constants. And then I divide it by big D. I call that big D, lovingly. Now, this capital D is the determinant of the coefficient matrix. That's the determinant with nothing changed out of the coefficient matrix. A1, B1, A2, B2, and we find the determinant. Let's practice it. Go ahead and turn over your paper today. This is your first option, right? 2x plus y equals 10, 3x minus 2y equals 8. Perfect. All right, so my first step is that I have to solve for big D. Okay, my determinant of the coefficient matrix is going to look like this. Now, first off, are they both set up in standard form? Okay, life is good. X, y constant, X, y constant. Perfect. 2, 1, 3, -2. I don't touch the constants yet when I'm looking at big D. Then I find the determinant of that coefficient matrix. Well, that's -4 minus 4. Everybody follow me there? 2 times -2 is -4, minus 3 times 1 is +4. -4 minus 4, big D is -8. Questions there? We good? Look what's up.
Why would 1 and 3 be -4?
It's always subtracting.
Okay.
It's the difference of. That was the rule for the determinant. It's always subtraction. Does that make sense? Yeah. Okay, so how do I find my x coordinate now? That's prep work. How do I find my x coordinate? Well, I know I'm going to divide by d. Right? Okay, so what am I going to divide by d? Well, I'm going to find the determinant of, okay, from finding the x coordinate, I replace the x values with the constants. Everybody follow me there? I took 10 and 8. I removed 2 and 3 and made it 10 and 8. The y coordinates keep their coefficients. Okay, so now we find the determinant on the numerator. So -20, I'll work it out here. -20 minus 8 over -8. That's not coming out right. Not nice. I thought that would come out nice. Huh, I guess not. -28 divided by -8. What's that come out to be? 3.5. What's wrong? What did I do wrong? Holy chicken nuggets, man. That's what's wrong. Whew. I was like, why is it coming out to a decimal? This is not. Oh my gosh. 3 times 1 is 3. Thank you. That's why you were like, why is the 4 negative? Shouldn't it be a 3, Mr. Lavery? Whew. I know, you guys just were like following up. Well, when you're doing something new like this, it's like, I must believe him that is actually, I know, really, and I just totally deceived you. That's why I was like, this should not come out to be a decimal. I don't remember this being a decimal. Because it's not a decimal. It's +4, right?
Yeah.
All right, so now we find the y coordinate. We divide by -7. And now when I make my numerator matrix, when I find my numerator determinant, I keep the x values, 2 and 3. And now the ones that get replaced are the y coefficients. So the 1 and the -2 go away and get replaced by the 10 and the 8. And now I cross multiply and subtract. 16 minus 30. I bet all those people watching at home are like, whoa, what the heck? Why is that a 4, not a 3? So we got negative 14 over negative 7, so positive 2. Let me check my work. 2 times 8, 3 times 10, negative 14. Okay. Now, here's the cool thing about this. So my answer is 4, 2, right? That's the location where these two lines would cross. Here's the cool part about this.
Pardon the interruption. This is for 7th graders with last names beginning with D through H. At this time, please report to the PAW for your health screening. Do not bring your book bag or personal belongings inside to the PAW. Remember to maintain proper social distancing. Please pick up your health screening form from the table in front of the PAW entrance. That's 7th graders, last names beginning with D through H. Thank you.
Welcome. Now, as I was saying, the cool part about this is that did X depend on Y? No. Like, if I get X wrong, does that force my Y to be wrong? No. Which, when we were doing substitution and elimination, if you got your X wrong, did you get your Y wrong? Yes. Then there was no other way around it. Now, okay, if you get your first determinant wrong like I did, then that's going to mess up your X and Y values. But X does not depend on Y. They are independent from one another. So it's kind of interesting to hear that we don't need X to solve for Y or don't need Y to solve for X. Okay, let's do another one of these. Try this one. Okay, so first off, is this set up in standard form? X, Y constant, X, Y constant. Good. So now, big D determinant, 1, -1, 2, -1. Everybody follow me there? Multiply, I got 1 times -1 is -1, 2 times -1 is -2. Okay, I believe we have a +1. Did you all get +1? Woo! Hey, I can do math. So I know my X coordinate is going to be something divided by 1. I know my Y coordinate is also going to be something divided by 1. My numerator determinant for my X is going to be 3, -1. -1, -1. Again, I take my X coefficients, my 1, 2 go away. It gets replaced with my constants, 3, -1. Now my Y determinant becomes, the X coordinates stay there, the X coefficients stay there, the Y values go away, the -1, -1 goes away, becomes 3, -1. So you can set them both up like that, and then just work run the numbers here when we get it all set up. So I've got -3 minus 1 over 1, right? -3, -1 times -1 is +1. So -4 over 1, so -4. -1 minus 6 over 1. Yep. So -7 over 1, -7. -4, -7. I mean, guys, that's actually pretty slick. Because finding the determinant can go pretty easily. Here's the issue, though. If it's set up in standard form, it's usually easiest to solve by elimination. And you have to have standard form to be able to do Kramers rule. So, I mean, unless I tell you otherwise, maybe don't use it, but I don't know. We'll see. In some cases, it is easier. Now, do they always cross at one point? No. So let's talk about those special cases. Well, you can use Kramers rule to tell whether the system represented has one solution, no solutions, infinite and many solutions. And here's how. Okay. It's all got to do with D, the coefficient matrix determinant. Okay, if D is non-zero, as long as D is not 0, you're going to get one solution. Okay? If D is 0, you either get infinite or no solutions. If D is 0, it's a special case. So how do you tell the difference between infinite and no solutions? Okay, well, if D is 0, and at least one of the x or y numerator determinants turn out to be 0 as well, then it's infinite solutions. Because you're going to get like a 0 over 0, which is infinite, rather than no solution. Okay? So when I go to solve my x and y, if these numerator pieces in here, if either one of those turned out to be 0, then it would be an infinite solutions. If neither one of them did, if neither numerator determinant is 0, then it's a parallel line, then it's a no solution. Okay? So again, when you get big D to be 0, it's a special case somehow. Okay, use Kramers rule to solve the system of equations. Now, first off, is this set up? No. We have to get this set up, right? Just gonna make sure it's the same for me. So I've got to get this set up correctly. So I'm going to manipulate this a little bit. Let's say we've got 3x. I need to subtract the 2y over to the left side, and I would end up subtracting the 5 over to the right. So we have 3x minus 2y is equal to negative 5. I would add the 9x to the left side. I would have a positive 9x minus 6y. I'd have to subtract the 15 to the right side, minus 15. Questions? Okay, let's find big D. Okay, that is 3, negative 2, 9, negative 6. 3, negative 2, 9, negative 6. So I've got a negative 18 minus a negative 18. Okay, my big D determinant is 0. So alarm bells are ringing. I know that this is a special case. It's either infinite or no solutions. So let's check and see which one it is. Well, let's find x. Let's start with x. You know I would put it over 0. I know that's kind of weirds me out too, but let's just have it right there for right now. And now for x, I replace the 3 and the 9 with negative 15 and negative 5, negative 5, negative 15, and we keep the negative 2, negative 6. So let's see what happens in the numerator determinant. If this comes out to be 0, it's an infinite solution. Let's see what happens. So we have a positive 30 minus positive 30. I get a numerator determinant as 0. So that means infinite solutions. Coinciding lines. Consistent dependent. I don't even need to check why. So as long as one of them turns out to be, one of the numerator determinants turns out to be 0, then it's an infinite solution. Questions about that? So now we have said, okay, we can solve systems by substitution, by elimination, by graphing, and now by Kramers rule. Okay, Kramers rule. This is only for 2x2s. Once we get into 3x3s, remember solving for a 3x3 at the beginning? We did section 3.6, and it was like we only had 3 problems for homework, and it took a really long time. Tomorrow, we're going to learn how to use determinants to solve those 3x3s. It doesn't really reduce the time length of the process, but at least it's another option that you can have if you want to. All right. So long, everybody at home.